Hello, today we'll see a NAND gate as universal gate. What is a universal gate? A universal gate is a gate which can implement any boolean function without the use of any other gate. So we'll see today we have two universal gates, one a NAND gate and a NOR gate. In today's video, we'll see a NAND gate as universal gate. So we are going to perform basic gate function using only NAND gates. Firstly, NAND gate as NOT gate. We know that a NAND gate has a minimum of two inputs A and B, and the function performed is A dot B complement. And we also know that we have for a NOT gate only one input A and the output is going to be Y is equal to A bar. Right. Now in the NAND gate circuit, replace B by A. When we replace B by A, we get it as A bar complement. This part of the circuit performs A dot A according to Boolean function. A dot A is A, right? So this is equal to A, and a complement we should get as A bar. So general representation of a NAND gate as NOT gate is shorting both the inputs and giving it to input A, wherein your Y is A bar. So this circuit is using one NAND gate to implement a NOT gate. Second, we'll see a NAND gate as AND gate. Right? We have two ways of doing it. First one is taking the expression y is equal to A dot B, which is an AND function. Complement on both sides. When you complement it on both sides, you have y is equal to A dot B complement. Whenever you're implementing any gate using a NAND gate, right, you have to get the relationship between two variables or between two terms as dot and complement. Here in this example, you can see that between two variables, that is A and B, there is the relationship dot and complement, which can be implemented using a NAND gate. I have y but in its complement form, but y should be in its original form. So to get it in its original form, complement it again on both sides. When you complement it again on both sides, you get y double bar, which is equal to A dot B complement and whole complement, which implies y is equal to A dot B double complement. Now I'll go for implementing it. Firstly, I'll implement this part of it, which is A and B given to a NAND gate gives me A dot B complement. Then I have another complement. This can be done by using a NOT gate, but we know that whenever we are implementing NAND as universal gate, the gates that to be used is only NAND gates. So this can be replaced by A, B, a NAND gate, A dot B complement, where a NOT gate can be implemented using one gate. That is our first example. Yes. So when we replace the NOT gate, we short both the inputs and give it to a NAND gate, which performs A dot B complement and complement. We have A double complement is A. Therefore, A dot B double complement is A dot B, which is an AND function. Next, in our video, we'll see the third one, NAND as OR gate. When you have NAND as OR gate, first we have for an OR gate y is equal to a plus b, and when implemented using NAND gate, we should have the variables and relationship between variables to be dot and complement. So complementing it both the sides, you have y complement is equal to a plus b complement. Now we wanted it in the form of dot and complement, so we'll apply De Morgan's theorem. When you apply De Morgan's theorem, you get y complement is equal to, we have De Morgan's theorem as x plus y whole complement is equal to x complement dot y complement. So using this here, you get it as a complement dot b complement. Now when you check this expression, y is in its complement form and the two terms are related with a dot. But when we have to implement it using a NAND gate, we wanted it in a dot and complement. Now we get y bar is equal to a bar dot b bar, but it is not in the required format. So we'll complement it on both sides again. When you complement it on both sides again, you get y double bar, which is equal to a bar dot b bar whole bar, which is y, which is equal to, you have got this here as dot and complement. This is one variable dot another variable with a complement, which can be implemented using a NAND gate. Now we'll see the implementation. I have the first term a, which is complemented, again b, which is complemented, and the relationship between the two is a NAND function. But whenever we are using a NAND gate as universal gate, we should use only NAND gates, and thus this NOT gates are to be replaced with NAND gate. So this becomes a NAND gate as NOT gate is shorting both the inputs, and B as it is shorting the inputs, and the output of it is given to a NAND gate. If you see this, it is A complement, B complement, and this performs A complement dot B complement whole complement. That is, if I apply De Morgan's theorem here, it is A double complement plus B double complement, which is A plus B, which is a OR function. Right. Next we'll see an NAND gate as XOR gate. In this circuit, I'll draw the circuit and try to get the expression back. Now, this is a circuit of an XOR gate using NAND gates. Let me call this as gate 1, 2, 3 and 4. We know that for an XOR gate, the output is A bar B plus A B bar. It is A bar B plus A B bar. Here, if I take the inputs as A and B and check the output at gate 1, gate 1 performs NAND implementation, so it is A dot B complement. So here I have A dot B complement. So one of the inputs to gate 2 and gate 3 is A dot B complement, with the other input to gate 2 as A and to gate 3 as B. If I check gate 2, gate 2 performs another NAND gate. It's a NAND gate, so performs complement of AND function. So it is between A dot B complement whole complement, which is A into, I'll apply De Morgan's theorem to this particular term. When I apply De Morgan's theorem, De Morgan's theorem says x dot y complement is equal to x complement plus y complement. According to this, you have a complement plus b complement, the whole complement. That is this complement. So you get this as a into a bar plus a b bar whole complement. We have, according to Boolean algebra, a bar to be 0. So this term is 0. This leads you to a b bar whole complement. So output of gate 2 is a b bar whole complement. Now similarly, if you check the output of gate 3, the inputs to gate 3 are b and AB bar. It is AB whole bar, and this is performing a Nand function, so it is with a complement. Similarly, when I apply De Morgan's theorem here, it becomes B dot A bar plus B bar whole complement, which is equal to A bar B plus BB bar whole complement. According to this rule, A bar equal to 0, we have BB bar going down to 0. This leads to A bar B complement. So output of gate 3 is A bar B complement. Now if you check the output at gate 4, you have one of the input as a b bar complement and other input as a bar b complement, and the relationship is a Nand function, so it is a dot and a complement. Now when you simplify this, I'll apply De Morgan's theorem to this. When I have De Morgan's theorem, I'll take this term as x and this term as y. We have x dot y complement to be x complement plus y complement. So this becomes AB bar complement plus A bar B complement. So when we have A double complement is equal to A, so this term becomes AB bar plus A bar B. That is, these two complements gets cancelled. So you have the output of gate 4 as A B bar plus A bar B, which is an XOR function. So that is A bar B plus A B bar, which is an XOR function. Right? Now we'll see the next one as X NAND gate as X NOR gate. Right? This is similar to that of your XOR gate with an added gate, with an additional gate. Right? We have an additional gate here. This is the circuit of this is similar to your OR gate except for gate 5 being added. Now in the previous circuit, we have got the output of gate 4 to be A bar B plus A B R, and we know when both the inputs of a NAND gate is shorted and given to a NAND gate, it functions as a NOT gate complementing the answer. Now with this as a condition, you have the gate 5's function to be A bar B plus plus A bar B plus A B bar whole complement, because this complement is you're using a fifth gate to be a NOT gate. So when I apply De Morgan's theorem, it becomes A bar B complement into A B bar complement, that is x plus y complement is equal to x complement plus x complement dot y complement. So this becomes A double bar plus B bar into A bar plus B double bar. So this is a plus b bar into a bar plus b, which is a bar plus ab plus a bar b bar plus bb bar cancels. This leads you to a bar plus a bar b bar, which is your XNOR function.